So now let us start with a new topic, which is principle of mathematical induction. Okay, all of you know what is recursively defined function on natural numbers. You remember that? Yeah, you start somewhere and then you have a rule how to go forward. And then the principle of mathematical recursion or principle of recursive definition of functions will allow you to define a function on entire omega or natural numbers. At that same time, we said that to define something for all natural numbers, we need recursion, and to prove something for all natural numbers, we need induction. So this is the exercise for induction. What are the main steps that you had to prove it for base case? Right? So base case is, in this case it's 1. Yeah, and then from the base case, like there is another induction case. Like if you know the statement is true for m, then you prove it for m plus 1. Okay. And you just have to write it down properly. All of you know how to do this. What about the second one? Will this work? Will this same idea work? Anybody who has finished second one?
We can suppose for 2 base cases.
Or just assume it to be true, like for
Okay, even if you assume for 2 base cases, yeah, I mean you can do finitely many base cases by hand. I don't have any problem. But then what will you do?
We assume for n minus 1 and then 2 for n plus 1.
You are assuming what?
We are assuming that it is true for n minus 1 and n minus 2 and then prove it for n.
Yeah, so assuming it for n minus 1 and n minus 2 and proving it for n. Is this really a valid method of proof? Can you assume it only for some specific numbers that you want? Like only previous 2 cases. Can you assume that?
yeah, why not? We're assuming only for the previous one case. It's the same thing. Like
No, I mean when you are saying that here we are only assuming it for one case and then proving for the next, then assuming 2 cases and then proving for the next, they are same. But that needs a proof that these 2 methods are the same. See, if I want to prove a statement for m plus 1 and I assume the statement for all numbers less than m plus 1, and using that I can prove it for m plus 1, then I should be done. But in mathematics this is called strong induction. Weak induction is when you have one-step induction. It's a domino effect. All of you know dominoes? Yeah, dominoes are like dice. Yeah. So if you have arranged dominoes in a sequence, if you drop the first one, then the first one will topple the second one will drop the third one. So it's a chain effect, ladder effect. However, this one-step effect is called weak induction. And when you assume it for everything below it, below that number, then it is called strong induction. So let me write down these 2 properties. So here we can use weak induction, and the method of proof we need here is called strong induction. Okay, so let's do that. What is principle of weak induction? I am just going to call it W of P for a property P. I want to prove something. Like the property P is true for all natural numbers starting from a certain stage. So therefore I am going to write it weak induction principle for property P, W of P. Okay, my starting step could be called K0. So I am just going to write down what this says. Yeah, so if P of K0 is true, this is my base case, and for all M bigger equal K0, whenever the statement P is true for M, then I can prove it for M plus 1. Then from this entire thing I can conclude that in fact the statement P is true for all natural numbers, maybe I should, for all natural numbers bigger equal K0, the statement P n holds. Any problems reading this statement? Base case is true and one step induction case is true. Then I can get the conclusion for all. Yeah, recursion also had a similar principle. If I know how to define the next step using the previous steps, then I can define it for all. Yeah, the so on part. Same thing. This is our principle of weak induction. And on the other hand, let me write down the principle of strong mathematical induction. I am going to call it S of P for a property P. Okay, so again it starts similarly. Suppose it is true for P of, suppose the property P is true at K0, some base case, and for all M bigger equal K0. Now I am not assuming just PM, but I am going to assume a big conjunction, big AND. Yeah, so I will say K0 less equal J less equal M and PM. So I am assuming that all the things from K0, like the property P holds for K0, K0 plus 1 ... up to PM, whenever this thing happens, then PM plus 1 is true.
That should be PJ.
Oh yeah, PJ, sorry. Thank you. This should be PJ. Then PM plus 1 is true, and whenever this happens, like the base case and the strong induction hypothesis is true, then we can again conclude that for all n bigger equal K0, Pn is true. So which of these two statements is stronger? Well, doesn't the name suggest that? Now this is weak induction, this is strong induction, so strong induction should be stronger, but it's not. They are both, in fact, equivalent. Whatever method of proof you may use, yeah, you are going to get the same answer. Okay, so this is our main job today, that will prove that these two statements are equivalent. But before we do that, yeah, we have to understand a bit of rules of logic. Because what does it mean that principle of strong induction implies principle of weak induction? Let us discuss that. So you are given the principle of strong induction and you want to prove this. What does it mean to prove this? The principle of weak induction, what is the meaning of proving it for property P?
Using a series of implications to get that.
Using a series of implications, and what is given to us, see, the principle of weak induction or principle of strong induction are both statements of type A implies B. right? So A implies B. This is also A implies B. This is also C implies D, let's say. Okay, let me write it down. We are going to use these statements. So this is of the form A implies B, and this is of the form C implies D. A itself can be broken down into two pieces, yeah, A0 and A bar. Okay, so this is my A0 and this is my A bar. And this is my C0 and this is my C bar. So A0 stands for base case, C0 stands for base case of strong induction, and these are the inductive steps. Okay, so when we say that we want to prove A implies B, then what should we start with? A. Exactly. We should start with A and then prove B. Okay, so whenever we are showing so we want to show strong induction. This should be the easy part, right? Strong induction should imply weak induction, as the name suggests. So strong induction implies weak induction. So first of all, we have to choose a property. So property is P. Okay, so assume for a property P of natural numbers that strong induction like S of P holds, i.e., I'm just going to call it Cp implies dP holds. Yeah, C is a statement which has P as a parameter, P as a variable. So therefore I am writing it as Cp and implies dP. You agree with that? Okay. And to prove weak induction, to prove Wp, we should also assume what should we assume? A of P. Okay, so what are we given now? We are given A of P, then we are given C of P implies D of P, and we want to prove B of P. But also note, this is a note here. So note that B of P is same as D of P. Is there any change in between B and D? No. So it will be sufficient. So what are we given? Cp implies dP is given, AP is given, and we want to prove BP, which is same as dP. Now there is a rule in logic which we'll study in logic part properly. So this rule is called modus ponens. MP. It says that if alpha is true and alpha implies beta is true, then you can conclude beta is true. Very good. Okay, so what is our situation right now? We know that C of P implies D of P is true, and A of P is true, and want to prove that D of P is true. So using modus ponens, what is sufficient to prove? Just Cp. If Cp is true, then using modus ponens, Cp is true and Cp implies dP is true. Together will imply that dP is true. Okay. So by MP, enough to show that Cp is true. But Cp is C0P conjunction C bar P. Okay, so I'm writing this, hopefully you have finished, and I'm going to go back. Observe, C is C0 conjunction C bar. We want to show that C is true, Cp is true. So, when is a conjunction of those of two things true? When both of them are true. Yes, so we need to show, so therefore we need to show that C0P is true and C bar P is true. Everybody is with me still? Right. Okay, so C0P is true and C bar P is true. What is C0P? Observe. C0 of P is same as A0 of P, and that is given to you. Yeah? Since AP equal to A0P conjunction A bar P is true, both A0P and A bar P are true. Moreover, C0P is equal to A0P, and hence C0P is true. So I am going to put a tick mark to this. C0 of P is true. We have proved that. Now what do we need to prove? C bar P is true. Okay, let us look at what is C bar P. We need to show for all m bigger equal K0, whenever this conjunction is true, then Pm plus 1 is true. So when we want to prove something for all m k bigger equal K0, we should choose some m and prove it for that, and it will automatically follow. Correct? So we should choose an m and then assume this side and then prove the right hand side. Okay. So to prove C bar P is true, assume that for any m bigger equal K0, this is true. K0 less equal j less equal m Pj is true. Okay, so all of these things are true. Conjunction is true means all of them are true. So in particular, Pm is true. In particular, Pm is true. But what do we know from the previous screen? If Pm is true and Pm implies Pm plus 1 is true, then by modus ponens, Pm plus 1 is true. Okay, so by, I'm just going to write by A bar P and MP modus ponens, Pm plus 1 is true. And therefore we are done. Yeah, therefore C bar P is true. You understood the idea of the proof? Okay, it's long but straightforward once you understand rules of logic. Yes.
Can you repeat the last C dash part?
Okay, so C0P is true, that's clear. So C bar P is true because what is C bar P? Let me go back here. We are supposed to assume this part. For any m bigger equal k0, if I assume the left the left hand side of the implication, I need to prove the right hand side. Okay, so I assume that the left hand side is true. So that big conjunction is true, which means in particular PM is true because it's in the conjunction. Now PM is true. Okay, now go to A bar.
A dash was true.
So A bar says that for all m bigger equal k0, if PM is true, then PM plus 1 is true. And you know PM is true, therefore PM plus 1 is true. Therefore, this conclusion of C bar P is true, and we are done. Okay, very good.
So, but we use the assumption that this k naught less than j less than m is true. We use this assumption and then we prove it.
Yeah, because this whole sentence, see, unlike any science theories, mathematics is always about if this then that. Mathematics never claims anything to be true. Okay? Science theories might do that. Theories of acids, Arrhenius' theory of acids and bases. It will say that if this particular substance is an acid, this particular substance is a base. Mathematical theories don't do that. It's always what should I say? Very honest. If this is true, then that is true. Yeah. We don't try to make any big claims.
So we could have used the fact that a naught is true. So m is equals to k naught, this is true.
Huh.
And then we could have followed on kind of induction.
No, we don't want to use induction to prove two inductions are equivalent. Right? Yes, I mean when your m happens to be equal to k0, then it follows from C0 that the left hand side of this implication is true, and therefore the right hand side is true.
Sir, why can't we do that? Like, induction is an axiom, so it's not circular.
No, I'm not trying to say it's circular, okay? Don't confuse anybody by saying that. Yeah? I'm just saying that these two statements are equivalent. Yeah? Even if it's considered as an axiom, we still need to prove that these two are different axioms, but they are equivalent.
Why can't we use induction to do that?
No, we don't want to use induction to do anything. Okay, so is this okay? Now, the harder part, slightly harder part, is to show that weak induction implies strong induction. So let's do that now. So weak induction implies strong induction. However, we cannot proceed directly. We have to define a new property. So given a property P, define a new property Q by Q of M for M bigger equal K0 if and only if conjunction Pj K0 less equal J less equal M. Okay, so we are not really cheating, but observe this. Yeah, so Q of M is defined to be this conjunction. So the property is true for, property P is true for K0, K0 plus 1 dot 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 up to M. Okay, and we are only defining it for M bigger equal K0, not doing anything. So what we will show indeed is that, so we will show that W of Q, if W of Q is true, then S of P is true. Understood? See, principle of mathematical induction is a statement which says that for all properties P of natural numbers, the statement is true. So I can choose something different. Like for proving property S of P, I can use a slightly modified property Q to prove the same statement. Because there is a quantifier, yeah, for all properties P. So for all properties P means in particular it is also true for Q.
Are you proving for the same property?
We will prove S of P. That's what you want to prove, correct?
But for the same property, we have to prove it.
Yeah, P is given and I want to prove strong induction for P. But I am slightly modifying the property to Q and I will assume the weak induction principle for Q. Okay. Now, first of all, you all know that B of P is same as D of P. Let me go here. B of P and D of P are same. But now I am going to claim that B of Q and D of P are also same. Observe that. B of Q. What is Q? It's true for all of them. Yeah, I mean put here. Maybe I should write it in a different color. So if I am saying for all n bigger equal k0, conjunction of k0 less equal j less equal n of p of j is true. This is logically the same thing as saying that for all n bigger equal k0, p of n is true. Right? I'm just saying it in a more complicated manner, but it's the same. So, okay, note that B of Q is same as D of P. Okay, so like before, we are given that the principle of weak induction is true, given that AQ implies BQ is true, and CP is true, we want to prove that DP is true. But DP is same as BQ is true. Now using modus ponens, what is sufficient to prove? AQ. Okay, good. So using MP, it is sufficient to prove that AQ is true. Yeah, because if AQ is true and AQ implies BQ is true, then BQ is true and BQ is same as DP. Okay, what is AQ? Once again, yeah, A0 of Q. Well, observe that please. What is A0 of Q? C0 of Q or C0 of P, both of them are same, right? Look here, what is the property? It is here. So that conjunction when m equal to K0 is just singleton. Yeah, I mean it's just PK0. So A0 of Q is equal to C0 of P is true. Yeah, since CP is true. So again the problem is only in the part A bar. Okay, so what is A bar of Q? Yeah, to prove A bar of Q is true, assume for some m bigger equal k0 that Q of m is true. But what is Q of m? Look here. Q of m is this conjunction. That is precisely this part. This is Q of m. Right? So therefore, if this is true for some m, then what can you conclude? Pm plus 1 is true. So by C of P, I should use black color again. So by C bar of P and MP, what will I conclude? That P of m plus 1 is true.
So A bar P and MP.
Sorry?
So A bar P and MP.
A bar P and?
MP. That was using the property of A bar P.
No, I am given C of P is true. So therefore, C bar P is true. C0 and C bar are true. So I am using C bar P and then modus ponens to conclude that P m plus 1 is true. Please have a look here again. Yeah, this is C bar and I am assuming the green circled part. Okay, so what is given? That P of m plus 1 is true. But what is finally? But Q of m plus 1 is actually Q of m conjunction.
PM plus 1.
So now Q of m is already assumed to be true. We have proved that P of m plus 1 is true, and therefore Q m plus 1 is true. So what did we finish proving? Therefore A bar Q is true, and we are done. So both these principles of induction are actually the same.